It's an honor to be speaking at this year's conference, and I'm grateful for the opportunity to share my thoughts and research with such a distinguished group of experts. The main three aspects of my paper are introduction, methodology, and experimental results. Firstly, as the development of the new generation of information technology continues, manufacturing is experiencing a transformation from the physical world to the information world, achieving interconnection and intelligent operation between the physical and the information worlds. This has become a trend in the world's industrial development. One important component of intelligent manufacturing is automated assembly lines. With the widespread use of automated assembly lines, large-scale production demands can be met, significantly improving the economic benefits of enterprise. However, traditional workshop monitoring methods mainly rely on manual recording, two-dimensional reporting, and configuration monitoring, resulting in poor real-time performance and visualization effects. In this paper, we utilize Unreal Engine 4 and 3-dimensional point cloud data to construct a one-to-one virtual space of the real physical space. Through real-time data transmission, we can remotely monitor the working status of robots on the production line in the three-dimensional virtual space, achieving transparent and intuitive monitoring of the production line, and ultimately realizing the integration of the virtual world and the real world. In this paper, we propose a digital twin smart factory virtual monitoring system based on the five-dimensional model. The system architecture is divided into 5 layers, namely the physical layer, transport layer, information processing layer, virtual layer, and application layer, as illustrated in the following figure. The physical layer serves as the foundation of the entire framework, consisting of the production environment and various devices such as robots, control cabinet, and sensors. By transmitting operational data from sensors in the physical layer to the virtual layer or through the transport layer, real-time data mapping between the two layers is achieved. The information processing layer plays a crucial role in processing, transforming, and fusing data collected from various sources to generate valid data that can drive the digital twin. The virtual layer is an essential component of the digital twin smart factory virtual monitoring physical system, providing a realistic representation of the physical layer and its dynamic and static characteristics. The application layer serves as the user interface, providing functions such as three-dimensional visual monitoring and operation status reproduction. Next, in this study, we propose a method to enhance the realism of virtual scenes by generating point point cloud data from static objects using radar scanning. The obtained point cloud data is then imported into Unreal Engine 4 with point cloud support, allowing us to extract accurate information about the size and position of the static objects. By utilizing this information, we perform secondary editing in Unreal Engine 4 to create a more realistic layout. Furthermore, to further enhance the realism of the virtual scenes, we add appropriate lighting and render the objects. The figure shows the physical space and the virtual space respectively. The right one is virtual environment construction, and the right one is the virtual space. Second, next, robot and efforts trajectory visualization refers to the process of visually presenting the trajectory of the robots and effector in the graphical format. By visualizing the end effector trajectory, it becomes easier to understand the robot's operational status and motion trajectory, which in turn facilitate the analysis and optimization of the robot's motion planning and control. In Unreal Engine 4, a particle system can be used to achieve the visualization of the robot's and effector trajectory, as illustrated in the accompanying figure. Next, the physical and virtual spaces are located on the different platforms, ROS and Unreal Engine 4, respectively, and thus it's essential to establish a communication link between them. The ROS platform's ROS Bridge offers a JSON interface between ROS and non-ROS platforms, making it possible to establish data communication between the two platforms using a variety of communication methods. In Unreal Engine 4, the ROS integration module is used to connect Unreal Engine 4 with ROS. Acting as a client in the ROS system, it connects to the ROS Bridge server using the WebSocket protocol as a communication intermediary, thereby enabling bi-directional communication between ROS and Unreal Engine 4. Train data is a critical component of digital twins, which includes both static and dynamic data that build the physical space. Static data encompass information such as the geometric shape, size, and layout of the device, usually transformed from real-world data captured by sensors. Dynamic data, on the other hand, is operational data generated during device operation and is a key part of achieving real-time mapping. In this paper, the dynamic data mainly comes from the UR5 robot and AGV car. The train data of UR5 robot includes current time step, joint name, joint position, joint velocity, joint acceleration. The dynamic digital twin data of AGV includes time step, position, and direction in the space. About the experimental results. The experimental procedure is to send a motion command from the controller to the robot drive, which drives the robot's motion. The entire operation of robot is monitored in the monitoring system. The virtual model successfully tracks the robot's movements and displays the real-time operational status of the device entity. To demonstrate the real-time capability of the digital twin system described in this paper, we have collected the time steps of 4 adjacent data points in each of the 3 stages, with the system runtime as the reference 0 point. The time steps are listed in Table 1. Based on the table, it can be observed that the average time intervals between adjacent data collections for stages A, B, and C are 0.207, 0.204 seconds, and 0.167 seconds, respectively. This further confirms the excellent real-time performance of the proposed digital twin system in this paper. During this experiment, the robot's real-time data was recorded while it was in operation. This data was later called from the system's database to reproduce the robot's state and verify whether the reproduced state was consistent with the actual running state. To ensure data accuracy, the historical data was compared with the real-time data sent by the controller. For instance, Table 2 shows an example of historical data fields, J1 angles to J6 angles, representing the received angle values in degree for each of the 6 axes, while the Table 03 shows the real-time data sent by the controller. The above data was imputed into the formula for mean absolute percentage error, and the calculated error between the replicated state and the actual operating state was only 0.1465%, and demonstrates the reliability and accuracy of the data. Thank you for your attention. That's all my content of my paper.